Hi guys, hello everyone. In this video, we are going to discuss about the resonance effect or mesomeric effect. Already we have seen in previous video, inductive effect we have already gone through. Electron displacement of electron displacement in organic molecules we have gone through already. Inductive effect. Now the second one is resonance effect, or we can say it as mesomeric effect. Okay. Yes. Let us see here. Second one, resonance. Resonance effect, or it is also called as mesomeric effect. Mesomeric effect, we can see here. Right. Now, yes, you see here, sometimes what happens is we cannot able to show the molecules only in one structure. Okay. Yes, because more than one structures involved in, okay, more than one structures have to be proposed. Means we have to propose more than one structure. It is possible, we can say here. That's why. But here the point is, if you propose more than one structure, all the observed properties of the molecule, okay, the properties of the molecule, no structure can be explained. Okay, you have to write the resonance structure, we can say here. Okay, the properties can be explained, referred to as resonance or mesomerism, we can say here. Okay, keep that in mind. That means you have to see that, right? I am writing that more than one structure have to be proposed, we can say here. More than one structure have to be proposed because it's possible to exist in more than one structure. Okay, but see, none of them explains all the observed properties of the molecule, but none of them explains all the observed properties of the molecule. Okay, yes, right. Here the point is observed properties of the molecule, because individual structure cannot explain, because any molecule, some of the molecules they can represent more than one structure, they can exhibit more than one possible structures, we can say here, but none of them they explains all the observed properties of the molecule. Okay, you can see here, but the solution is, what is the solution to this? You have to write the weighted average of all valid structures. Okay, we have to, the solution is, what is the solution for this? The solution is to write a weighted average structure, average of all structures, all valid structures, all the valid structures which explains all the properties, which explains all the properties. Okay, yes. Here average, you have to write the weighted average of all the structures, valid structures, keep that in mind. Okay, that is the point you have to keep in mind. Then only it explains, all the properties. This phenomenon is known as resonance. Okay, this phenomenon is known as what here? This is called resonance. This is called resonance or mesomerism. Resonance or mesomerism. Okay, keep that in mind. Right. Now, you can see here the resonance. What are the features? Silent features of resonance, and what are the conditions, features we can see here. Let us go through here. Right. Features of resonance. Different features. What it indicates. Let us go through that. Of resonance. Okay. Yes. Let us go through. Yes. Here, all these structures are whether they exist really. No. Those are called hypothetical structures. Okay, which structures those are? Hypothetical structures. These hypothetical structures, you can see here, the hypothetical structures with different arrangement of electron, but with identical, positions of atoms are called resonance structures or canonical forms. You can say here. Okay, right. The hypothetical structures with different arrangement, with different arrangement of electrons, but arrangement of electrons different. But see, positions are identical, but with identical positions. With identical positions for atoms. Atoms are, same positions. Atoms cannot be disturbed, but electron arrangement will be disturbed. You can see here. Okay, arrangement of electrons, different arrangement of electron, but identical position for atoms. Keep that in mind. Okay, atoms positions are remain same, but electron arrangement will be different. Keep that in mind. And those structures are called atoms are called resonance structures or canonical forms are called resonance structures. We call them as we refer as resonance structures. We can say here. Okay, or what we say resonance structures or canonical forms. Canonical forms you can say here are contributing structures. Yes, these are you can see here resonance structures, canonical forms. Resonance structures are also called canonical forms are contributing towards molecule. We can say here contributing structures towards molecule. We can say that right. Yes, you can see here The resonance structures are only imaginary. I said already, these are imaginary, we can say here. These are only imaginary, and the actual structure of the molecule is considered as hybrid. A hybrid of all valid resonance structures. Okay. The actual molecule, I'm writing here, the actual molecule is considered as the hybrid of hybrid hybrid of all the valid resonance structures. Oh, yes, you can see here. Okay, yes. The actual molecule is considered as, this is important, keep that in mind, the hybrid of all the valid resonance structures. Okay, yes, you have to keep that in mind. It is generally called as resonance hybrid. Okay, resonance hybrid, we can say here. It is known as, generally referred as, what here? It is known as resonance hybrid, referred as resonance hybrid. The actual structure is called as resonance hybrid, we can say here. Okay, right. Next one, you can see here. Right. Next, look at this. When you observe, the energy of resonance hybrid is always less. Keep that in mind. Less than what here? Less than the energy of any of the contributing resonance structures. Yes, it's valid point, important point. Keep that in mind. You see here, the energy of hybrid resonance hybrid is always less, always less than the energy of any of the contributing resonance structures, less than the energy of any resonance structures. Resonance structure. Okay, yes, let us see here. It is always less than, you see, I am writing the formulation. Resonance structure, resonance hybrid, energy of resonance hybrid, it's less than any of resonance energy of any resonance structure, you have to keep in mind. Okay, the point here you have to keep in mind, less. Resonance hybrid energy is less, we can see here. Right. Now you can see that the energy of resonance hybrid is always less, we know that very well. Okay, yeah, therefore the delocalization of electrons, how it takes place? Delocalization means what here? Delocalization is showing using curved arrows. What it shows? Curved arrows, we can say here. Right. Let us go through. Individual resonance structure do not exist and molecule do not resonate. Okay. Switch back and forth between the structures, we can say here. Hence, the delocalization of electrons is also imaginary process. Okay, which helps in understanding the resonance. Yeah, delocalization of electrons can be shown by using which arrows? Curved arrows, we can say here. I'll show you how it can be shown. I'll take an example and I'll explain that. Let us see here. Yeah, the delocalization of electrons. Delocalization means shifting of electrons. Shifting of electrons from one atom to the another atom, we can say here delocalization of electrons. Electrons is shown by using curved arrows. Okay, yes. How the delocalization takes place, I'll show you here. Let us take the, for example, take benzene here. You know the formula of benzene. Bonds are like this, you can see here. And shifting of this double pi bond takes place from this carbon to this carbon. Yeah, this arrow indicates the delocalization of electron. It to a back and forth, we can say here. What it is? Back and forth. Here it is negative charge and here positive charge. You can say here. Then what happens due to this negative charge? What happens here? Immediately, this is a process of delocalization. Keep that in mind. And how it can be shown, I'll show you. You see, here this process how it takes place. I'll show you. With expansion. Let us take this. Yeah. Now you see here the shifting of this bond from here to here, back and forth. You know. Yes. Immediately what happens since it is negative, this bond will be shifted towards this. You see, because it is shifting towards this. Therefore, here there is a positive charge. Electron shifting towards this carbon, that's why it is negative, and immediately due to influence of this negative repulsion arises. That's why here this electron again shifted away from this carbon. Therefore here you can see there is a formation of double bond, and negative charge comes here. You can see that. Okay, right. Now what happens here? This bond is again shifted towards this. Then what happens? Immediately you can say that since it is negative, again what bond is formed here? Since it is positive charge, because that electron shifted towards that, and the double bond here it is remains same, and here there is a double bond formed in between these two carbons, and there is positive and negative is there. No, here it is negative will become, yes, it comes here. Therefore now you can observe these two structures. This is initial structure, this is final structure, you can say here. And how it looks like, I'll show you here. Yes, you can see. Yeah, you can see that these two structures are called, you know also called as, these are resonance structures, but here these structures are given by the scientist name called Kekule. That's why these structures are called Kekule structures. Which structures? Kekule. Kekule structures, you can say here. Keep that in mind. Okay, this is the way you can write these two structures. We can say here that one more thing here we have to keep in mind. What we have to keep that in mind? Individual resonance structures do not exist. Yeah, keep that in mind. Individual resonance structures do not exist, and the molecule do not resonate between these structures. Hence, the delocalization is also imaginary process which helps in understanding overall structure. Okay, yeah, I'll write that point. Keep that in mind. All of you keep that in mind. These curved arrows, delocalization of electrons can be shown by which arrows? Shown by using curved arrows like this. These are all curved arrows. We can say here. You can see here, right? Now let us go through here. Right here, the individual resonance structures do not exist really. Though those are hypothetical, imaginary. Keep that in mind. Okay. Yes, I'm writing that point. All of you keep in mind. The individual resonance structures do not exist, do not exist, and the molecule do not resonate, and the molecule do not resonate. Resonate. Resonate means what here? Switching back and forth. Switching back and forth. Yes, back and forth means what here? This is called back and forth. Going forward, backward, back and forth. We can say here. Right. Keep that in mind. Yes. Actually cannot be. The molecule do not resonate. Yeah, do not resonate between these structures. It's very very important point. You have to keep. One can keep in mind. It's mostly a useful point. You have to keep in mind. Therefore, you can see that between these structures, between these structures. Okay. Hence, what we can conclude, hence delocalization of electrons is also imaginary process. Yes, here the important point you have to keep in mind is, hence the delocalization, localize and delocalize, keep that in mind. Delocalization means shifting of electrons from one atom to another atom. You have to keep that in mind. Yes, delocalization of electrons is also imaginary. Is also it's imaginary, purely imaginary. We can say here. Okay, is also imaginary. We can say here. Process which helps in understanding the resonance. Okay, delocalization of electrons is imaginary. It's they'll ask in exam. Keep that in mind. Delocalization of electrons. They'll ask in exam. Keep that in mind. Imaginary process. It is also imaginary process. We can say here, which helps in understanding the resonance. helps in understanding the resonance. Understanding the resonance, we can say. Yeah. Now, let us go through here examples. Let us see here. Just now we have taken benzene. Okay. The resonance hybrid of benzene is what? Just now we have written resonance structures of benzene. Then what is the resonance hybrid of benzene? Let us see here. Okay. You can see that very important point what you have to keep in mind. Resonance hybrid for benzene is what here? These are called resonance structures. Okay. You can see here. Aqueous structures, resonance structures, we can say here, resonating back and forth. It is imaginary only. Really, they are not exist. You know that very well. But what is resonance hybrid for this? The combination of these two you have to write. Resonance hybrid, what you have to write? Combination of these two. How to write? Let us see here. Now it becomes, yeah, you can see here. It is exactly equal to. This indicates exactly equal to the resonance hybrid of this. You can see here. I'm writing that. Yeah. Now, uh, see here. This is called resonance hybrid, or it can be written like this also. It can be written like this also. Yes. You see here, these structures are called ORR. You can write here also. Yes. These are. It is called resonance hybrid. What you can write here? Resonance hybrid of benzene. Actual structure of benzene is this one. Sorry, hybrid of benzene. You can say here. You can say that. In this manner, you can conclude resonance hybrid of benzene. You have to keep in mind. Okay. In that manner, you can write resonance hybrid of benzene. Okay. Right. Now you can see here the point. What you have to see, the actual structure of benzene is, you know, the see here it is every cc bond length how much it can be for resonance hybrid. Keep that in mind. The order of every cc bond is 1.5. Actually cc bond, bond order, you can say here bond length you have to consider, bond order you have to consider, and you see the bond order is of cc bond. I'm writing the point here. The bond order here, it is also important point. The bond order of cc bond in benzene. cc bond in benzene only it is. In benzene is, you can see here, 1.5. Actually one only, it should be one, because if two double bonds are there, bond order 2. If triple bond is there, bond order is 3. If single bond is there, bond order is 1. But here it becomes 1.5 due to this resonance. Okay, this resonance hybrid, due to resonance hybrid, the bond order becomes 1.5. It's very very important point, keep in mind. Okay. Yeah. Next one you can see here, bond order is 1.5. Let us see, continue this. Next, what about the bond length? Actually, bond length here, C single bond C bond length is, you can see that 1.54 angstroms. We can say that CC single bond. Generally, any organic compound, if you consider C single bond C bond length is 1.54. You can say here, and but C double bond C bond length how much? 1.2 angstroms. Okay. If you consider experimental data shown that, if you take here, for example, I'll show, let us take one structure, let us take like this, you see. Now here how many double bonds are there? How many double bonds are there? 3 double bonds are there. 1, 2, 3. How many double bonds? 3 double bonds are there. How many single bonds are there? 1, 2, 3. In between, this is carbon, this is carbon, this is carbon, so total 6 carbons are there. 3 double bonds and 3 single bonds. Okay. 3 double bonds, one double bond length, how much, Actually, C, C double bond C, C double bond C bond length, how much, double bond length, it must be always 1.20 angstrom units. Okay. And C single bond C bond length, how much, C single bond C bond length, single bond length, single bond length must be, you can see here, 1.54 angstroms. It must be there, it must be like this. But experimentally, actually these are also experimental, but when you look at the benzene, in benzene case, the bond length of CC bond length of all the, see, all the bonds, how many bonds? 1, 2, 3 double and 3 single, you know that very well. 3 double and 3 single, already we have seen, right? But all these 6 bonds in benzene, you see, I'm writing that point, it's also very, very important. But all the bonds, CC bonds, all the CC bonds in benzene has, all the bonds in CC in benzene, bonds in benzene have, they have how much, they have same and equal, you know, they have same. Total how many bonds are there? 6 bonds are there. 3 is double and 3 single we are assuming. But due to this resonance hybrid, they are same. It is very important, they are same. And how much it is? Benzene, they have same, you can see here, all the bonds are same. And the bond length is, it is experimentally, 1.39 angstroms. How much it is? 1.39. All the 6 bonds have 1 point, these are in between single and double bond length, you have to keep in mind. Double bond length is 1.20 angstroms and single bond length is 1.54 angstroms, but the overall here it is 1.39 angstroms, you have to keep in mind. Okay. Yes, due to this resonance, benzene can get extra stability. Okay, due to this, benzene can get extra stability and it can undergo electrophilic addition reactions, we can say. Okay, it do not undergo electrophilic addition reactions. If it undergoes electrophilic additions, you know, then what happens? The resonance structures or delocalization phenomenon will disturb. If resonance will be disturbed, then it is not stable. Okay, keep that in mind. Here the point you have to keep in mind, due to the resonance, I am writing that point here. It is also important, due to the resonance, benzene gets extra stability. Gets stability, extra stability. extra stability, 1 point. Okay, and the next, and it does not undergo electrophilic addition reactions, and it does not undergo electrophilic addition reactions. Keep that in mind. Electrophilic addition means what? See, due to resonance only it is getting more stability. If it undergoes electrophilic addition means breaking of double bond and adding of some compound, some substituent. You can say here reagent can be added. That's why reagent, if it goes and attacks, then the resonance will be disturbed. Okay, because double bond should be broken. One bond is one come here, and here when it is shifted in this manner, then you can see to the resonance process will be disturbed. If it disturbs, then it loses its stability. That's why here addition of means it is, if it is shifted, negative and positive charges will come here. A negative reagent comes and negative part of the reagent comes and added here at the positive position, and positive part of the reagent comes and added at negative position. Therefore, the resonance will be disturbed. Delocalization of electrons will be disturbed. It cannot undergo delocalization. That's why there is no. If it does not undergo delocalization, there is no resonance. Keep that in mind. If it undergoes delocalization of electrons, okay, then only resonance takes place. If resonance is there only, it gets more stability. Benzene will get more stability. Otherwise, it cannot be. Okay, that's why here, if it undergoes electrophilic addition reactions, then resonance will not be exist. Due to that reason, due to this resonance, benzene gets extra stability and it does not undergo electrophilic addition reactions. Okay, but it undergoes, but the point here, but it undergoes electrophilic substitution reactions. But benzene undergoes which reactions? Electrophilic substitution reactions. Keep that in mind. It does not undergo addition, but here benzene undergoes electrophilic electrophilic. You can see that substitution, electrophilic substitution. Keep that in mind. Reactions. Okay. Yes. Uh, this is the case you have to keep in mind. It's important. Okay, electrophilic substitution is very important. Keep that in mind. It undergoes electrophilic substitution reactions. Okay, substitution is means what here? Removal of hydrogen, and take H is there. Everywhere H will be there. H will be there. One of the reagent will be removed, and for example, you say NO2. Just its representation, removal of H takes place, minus H, removal of H takes place, addition of NO2 takes place. Yeah, all H will be like this. Just for example, I am showing just representation. NO2, you can say here. This is called substitution. And removal of H, benzene means actual benzene, it can be shown like this. 6 carbons are there. The benzene formula C6H6. Yeah, one of the H takes place, removal of one of H takes place, and it can be added C6. It can be substitution reactions, you can say here, C6H5NO2, C6H5OH, C6H5 CHO, C6H5COOH. In all these cases, what is going on? Removal of H taking place, some functional groups comes and substituted. Okay, that's why it is called substitution. Keep that in mind. Okay, yes. This is all for this video. Let us continue this in next video. Different rules for resonance and stability of resonance structures. We will go through that. We will discuss. Okay, thank you. It became already more.